We're getting closer to being able to render a three-dimensional scene using OpenGL. I must teach you about uniform data before doing that. Here is our triangle that we've been doing in previous videos. Hopefully this is old hat. Let me bring this chart onto the screen. This is our basic graphics pipeline where we send our vertex attributes in, run it through the vertex shader. Vertex shader outputs a position and screen space and the other data, which we've seen interpolated. In this case, we're interpolating the color data. Fragment shader runs for every possible fragment on the screen. And if those fragments become pixels, then we use those fragments, RGBA values, and write them to the color buffer. Hopefully that's all old hat. This data that we send in, these vertex attributes, is known as varying data because it varies per vertex. For example, this vertex right here, its position is -1 on the x, -1 on the y. That position is different than this vertex up here. This vertex's location is 0 on the x, 1 on the y, which is different from this vertex over here, which is +1 on the x, -1 on the y. Then their colors vary. The color for this vertex is red, and the color for this vertex is green, and the color for this vertex is blue. So we call that varying data because it varies from vertex to vertex. Uniform data, however, on the other hand, does not vary. It is the same for every vertex. Right? I'll write uniform data. We send that into the vertex shader, but that uniform data does not change. It does not vary from vertex to vertex. This data is the same from vertex to vertex over the duration of one call, and we'll look at what that means a little later in this video. For now, let's do a basic uniform and show you what we can do with that. The uniform I want to send in just for a hello world uniform, I want to send in a different color. I'm going to say, hey, all the vertices need to be red. We'll send in red. And so even though we have varying color data for every vertex, we will ignore that varying data, and instead we will use our red data to color each vertex, and we'll be back to a solid red triangle, even though we could have this pretty red, green, and blue. To declare a uniform value inside of your shader, it's pretty straightforward. The in keyword means we'll take input for the varying data, and instead of saying in, we're going to say uniform. And it will still be a vec3 for the color. We'll call it dominating color because this color shall dominate over the actual vertex color. Call it dominating color. And so the color, instead of saying vertex color and using the varying data, I will instead use the uniform data, which will be the same for every vertex call. So I'm going to grab this dominating color and I'll put it right here. Save our shader away. We need to send in this uniform data. Just like we did with the varying data, we have to send in the uniform data. And the best place, I think, to get started would be this paint GL. So we clear the buffer bit, the depth buffer, the color buffer, set up our viewport. So right here, I think we'll do our uniform data. I want to use vec3. Do not have a using for vec3. Let's put it, I'm using namespace standard. That's cool. Using GLM vec3. Vec3. Dominating color. And that one was 0.0f, 0.0f, 0.0f. Except I wanted it to be all red, so I will change this component to a 1, which means red is all the way turned on, green and blue will be turned all the way off. Now this vector3 that I've defined is sitting on our stack. I have to send it down to the graphics hardware, so the graphics hardware will place it right here. And the way I do that is by getting the location of this uniform inside of my shader. So let's do exactly that. GL int dominating color uniform location. That's a long variable name, but I hope it's descriptive enough, and I'm big on readability. GL get uniform location Get uniform location takes two arguments, the program ID and the name of the uniform I'm looking for. The program ID, we don't have it up here. I wonder, install shaders. Yep, I made program ID local to this function, but we actually need that same program ID. Remember, this program ID is the combination of our fragment shader and our vertex shader linked together. We did that a few videos back, so I'm going to grab this program ID. I'm going to copy this and not declare nor define program ID right here. I'll just throw it up here in static space. That's pretty trashy of me, but again, this is just some demo program we're doing. So then we will still set program ID right here when we create the program. And then when we actually get to paint, I'm going to say, well, inside of program ID, one of those shaders has a uniform. In fact, I'm going to do a new vertical tab group and push this off to the right a little bit, zoom out. Hopefully you're turned up to high definition. And let's say inside of this program ID, I know one of the shaders, could be either shader. In this case, we're using the vertex shader. There's a uniform called dominating color. Right, so dominating color. I have to send that in as a char star, and OpenGL will compare the string against all the uniforms in my program. There only happens to be one, so OpenGL will return the location of this dominating color. Now, what does it mean, location? For now, you can think of this location as just an ID. It's a handle to this uniform, the same as we have a handle to our buffers, a handle to our program. It's just a handle to this uniform. Later, when we study some nitty-gritty details of uniforms, we'll understand this is actually a register location. And so that's why they call it uniform location instead of ID. Uniform location instead of ID. Anyway, we have this handle to the location of dominating color, and we have a color here sitting on the stack that I want to send down to OpenGL. So I will say GL uniform 3F, meaning 3 floats. I want to send down a uniform value of 3 floats. Let's make sure it's cased correctly. Open parenthesis, the location. It says, which uniform location do you want? Well, it's the dominating color uniform location. So I'll paste that there. And then it wants floats 0, float 1, and float 2. So I could say dominating color dot red, dominating color dot blue, dominating color dot green. Oh, that's a mouthful. You know what? There's a different version of this GL uniform 3F. There's another one I can say 3FV, V standing for vector. And if I control shift space in here to show you the arguments, I have a count and I have a float star. I can pass a pointer to some floats instead of passing these floats one by one. So let me say 1 for the count, delete all this stuff, say dominating color sub 0, and take the address of it. The GLM vec3 type overloads the brackets operator and returns a reference to whichever float you request. And I'm going to request the first float, and I know that GLM vec3 stores its floats in a consecutive manner. So here are 3 floats, 4 bytes each, and the first one is my R, the second one is my G, the third one is my B. So I can get away with this. I can say, give me the address of the first float in there, and that is a float pointer. And look what OpenGL wants. It wants a const GL float pointer. What's the difference between a float pointer and a GL float pointer? GL float. I'm going to type GL float there, hit F12 on it. Look at the type def, and oh look, GL float is simply type def to a float on my platform. So we're okay, I can get away with that. So the V means vector, meaning I'm going to pass you a pointer to 3 floats instead of passing you 3 floats individually. This count is simply how many groups of 3 I'm sending down. I'm only sending down 1, but if I wanted to send down an array of floats of 3, I could, and so my count would change in that case. All right, I think we're good. We've just sent down red for the dominating color. And let's control F5 this, see what happens. Build started, build succeeded. Oh, look at that. We're not relying on varying data anymore. Okay, I just totally ignored our varying data. our varying vertex color, and I said we're going to dominate the color with this uniform value. And there you go. We're all red. Okay, let's try, I don't know. Let's try blue. Okay, no more red. We'll do blue. Control F5. Run this. And oh, duh. That was green, not blue. Dirt. And we can have all sorts of fun with this. Let's change this to a 0.5 on the blue and get a greenish, bluish looking. Yeah, there you go. Anyway, you have a heyday. So that's uniform data in a nutshell. It's uniform over the entire geometry. It's the same value for the entire triangle in this case. In the next video, I'm going to do one little more uniform thing just to kind of hit home with the difference between uniform and varying data. And then hopefully we can move forward to getting a three-dimensional cube to show up on your screen.